Right, good afternoon. Merci beaucoup pour la opportunité de présenter. Yeah, as you can hear, my French is not very good, but since I now count as American, my French actually is excellent. No, so, yeah, and this is the title for the whole lecture series, so I will start with more basic stuff. Yeah, for those remotely, sorry, at the moment, for this, the slides aren't yet available before because I had some trouble with my suitcase this morning, and, well, for the next days, I hope to have these things done. This is not to be a reading from the manual. If you have questions, please ask, and feel free to interrupt if you can't understand what I'm saying, if something is not clear or so, or if you have more specific questions, ask afterwards, and I'm happy to show you how things go. This is not intended to be one trip down the motorway, but a more touristy route with many things one can look at. So, the very first thing is I want to just talk a little bit, if you've never used the system, about how gap works, how one interacts with it. It's a text interface, as a lot of mathematical systems have, where you type in commands and you get answers. So here are just a couple of, you type the command, you end it with a semicolon, the output will be the object returned, and it prints it directly, and the commands have names which try to be comprehensible what they are doing. There is the particular one, last refers to the last output. That is very useful when working interactively. If you put a double semicolon there, it still does the calculation, just doesn't print the output. That can be useful if the output is very large. If you have longer input, you don't want to type it in directly, but you want to put it in a file and read in the file. There is a command read. Do we have some stick or pointer or so? Sorry. So there is a command read, which will read in a file. These files have to be plain text files. So if you are under Windows, you want a file which is a .txt file, not .doc or something. You might under Windows have to type the full path, and you might under Windows have to type it with a forward slash, even though normally you use a backward slash, and that's because the program originates under Unix. There is an online help question mark, and then a word gives you help about the command with the name you're giving. If you want all pages which contain a particular word, double question mark does more of a keyword search. log2, and then a file name will produce a transcript of your session to a text file if you want to go to afterwards. print2, append2. Print will create a new file, append will add to an existing file. One can output things. There is a command save workspace, which one can use to save the current state of the system, but that is a little bit tricky. It is not portable between versions of GAP or different machines, and using it under Windows is particularly tricky. If you're desperate to use it, ask me and I can show you how it goes. Oh, and the most important thing in the end, if you want to get out, quit semicolon or Control D exits the system. Yeah, the most important data type is lists, and that's because basically anything that is not any collection of objects, sets, vectors, matrices, they're all represented by lists or by things which behave like lists. GAP tries to store lists efficiently. It tries to be clever. It doesn't always manage on its own. One can help it but that basically you interact with these objects just as a normal list, and then there is a length, is the length of the list. Element access is with the square brackets and the index position. Yeah. One can simulate even objects which behave like lists, even though they are not, but we don't really need this here. Okay. Oh, yeah, and there is a technical limit for the length of the list, but I've never reached that limit. If you have a list, for lists also there are very convenient functions to do things with a list. For example, to go through, oh, I probably shouldn't walk out of the screen. To record, to go through a list of objects and apply a function. So, and similarly, you find elements with a certain property from a list, or check whether all elements in a list have a property, and one can use this essentially to write short programs without ever writing a for loop or so. So for example, here, this is an example of calculating all Carmichael pseudo-primes up to 2000. So I'm selecting with filtered from the numbers 2 to 2000 those which are not prime. That is this filtered command. So now this would give me a list of the numbers there which are not prime. And now I want for each of these numbers n that for all numbers from 2 up to n minus 1 which have GCD 1 with this number, that for all of these numbers b, I have that b to the n minus 1 modulo n is congruent to 1. That's the pseudo-prime property. And I mean, this is not the most efficient way of testing for it, but it's a very short way in terms of typing, and that would give me these numbers. GEP tries to do things in a way that one can justify the results. So the goal is that it will only return correct results, well, up to program errors or computer errors. But if it gives a result, it's in some way certified result. It is not just, it will, unless there are specific commands or it gives you a warning, the result is not just probabilistic. The output might depend, or the result might depend on sometimes on results of published classifications. So if you want to check the classification of finite simple groups, be aware that some algorithms actually use it. GEP also will try to answer the question you give it, even if it is hard. And that means it might allocate a lot of memory, even if it's hopeless. There is a safety catch where GEP tells you, oh, I ran out of memory. Do you want me really to continue? And I think it's about a 2 GB allocation. You can continue, but if you get that error message, sometimes this means that one had this means that in many cases that one might have asked something which one shouldn't, which it really can't do. It also tries, in general, functions will try to perform some checks on the input to make sure that things are correct or fit together. There is, for some functions, a version where the function name has an NC appended, NC for no check, to avoid these checks because they could be costly in certain cases. Okay. Right, so that's just the general thing. So what my plan is, the first lecture will talk about some basic ideas how one can represent groups on a computer and problems which arise there, the basic idea of the orbit algorithm and its variants. Then in the second lecture, I will talk about the particular cases of permutation groups and matrix groups and, well, I'll tell you later what the other ones do. So what is a group? A group is, if you take a textbook, it's a set of symmetries of an object. So for example, if we, at least the standard American textbook for abstract algebra, if we take the dihedral group of order 8, the symmetries of a square, there we have 8 elements in the group, where the textbook calls them R0, R90, that's the rotations. It has horizontal flip, vertical flip. Is it the axis horizontal or is the horizontal fixed? There are 2 diagonal flips. Which one is D, which one is D prime? What do you do if you don't have a square but say a hexagon? Then you get a D double prime. So that is really not a good way for representing a group. But what we want to do is we basically want an unambiguous way which extends to a large class, to basically all finite groups. So we typically would represent groups in one of 2 ways, either as transformations of existing objects, permutations of points, matrices, automorphisms of other structures, or, as we will see later, we represent groups through words in a generating set. And we will also, in Bettina Eick's lectures, learn about polycyclic groups with a PC presentation, which is a special case. Here the caveat is that basically whenever you make a new group, it's something which lives in its own world and a priori has no connection to other things. And there is built in, but it will build on either of these ways. There are various libraries of groups built in, which one can just use to get examples. These different representations are not all the same as far as efficiency goes. Basically, the PC presentation, the polycyclic groups work fastest, but that only works for solvable groups. In general, permutations are better than if you have a small degree permutation representation, that is better than a matrix representation, but it works faster. But not every group has such a representation. But these things are used. So GAP might, or in some cases automatically will, internally use a different representation to work with groups to actually work in another representation, and one can force this. There are in general also function isomorphism, and then say isomorphism perm group or isomorphism PC group for a solvable group, isomorphism FP group for finitely presented. They are the functions that do conversion between representations, and they return a homomorphism because typically you want some way to connect your original group with a new one with a different representation. Also, in a similar way, for factor groups, the way to work with them is that you take the natural homomorphism. There is natural homomorphism by normal subgroup, which gets a group and a normal subgroup, and then makes a homomorphism, the image of which is isomorphic to the factor group. Oh yeah, that basically says the same. This slide should have gone out. Sorry. Well, if you store elements, it takes space. So just as a very basic calculation, in 1 kilobyte of space, you could, for example, fit a permutation of degree 500 or a 90 by 90 matrix over the field with 2 elements. But overall, even if your computer is big, you have some finite amount of memory available. That means we only can store a finite number of elements of a group. Vice versa, or the other way around, if the group is very big, we can't store all elements. And algorithms in general try to avoid storing all elements. But what they will do is typically the goal is, if we have a group, we only want to store a generating set of the group, maybe a little bit extra data which supports things and supports the calculations, but definitely not all elements. So the first basic question is, what can we with a group if we don't have a list of elements, if we only have generators? How can we test how large the group is? How many elements does it have? How can we test whether an element is in the group? How can we evaluate a homomorphism if it is given by images of generators? That is, how can we decompose an element as a word in the generators? And that's the first questions to look at. And the tool for this is the one thing which is special to groups, which other structures don't, or other things don't necessarily have, and that is group actions. And that will lead us to the orbit algorithm, which is basically the one algorithm which is specific to groups and doesn't just work for, while some other tools we are using are tools also used in other areas, the orbit algorithm is specific to groups. So I have a group G that acts on a set omega. My actions here in the lectures and also in GAP are always from the right. Yeah, we want a group action. The identity maps every element to itself. A product acts as a product should do. And examples of this are permutations on point, matrices on vectors, automorphisms on the underlying structure, matrices on subspaces, and so on. And whenever we have a group action, there is the orbit stabilizer theorem, which tells us that there is a bijection between cosets of the stabilizer and elements of the orbit. And that's the first thing I want to do. I want to look at, if I have a group, I have a point, how can I find the orbit? And from that, how can I find the stabilizer? Yeah, I might want, find the orbit of an element, calculate the stabilizer of a point, and a problem which turns out to be interesting, in particular if a group is acting on itself. This is sometimes called the transporter problem. If I have two elements in an orbit, in a set which lie in the same orbit, how can I find an element which maps one to the other? Respectively, how can I prove that no such element exists? And of course, my input for groups and also the output of the subgroup should be not element lists, but generating sets. I want to give groups always just as groups generated by sets of elements. So let me start with a basic orbit algorithm. That takes a point, a group given by generators, and it calculates the orbit. And what is the basic idea? Well, the orbit is the set of all images. Every image is under any group element. Every group element can be written as a product of generators with repetition and different orderings. And because of the second axiom for group actions, if I apply a product of generators, I can apply each generator one by one. I should say here I'm always talking about generators. If the group, of course, I also might have inverses of generators. If the group is finite, that doesn't matter because an inverse is just the power of a generator. But if you have genuinely infinite groups, you basically need to make sure that your generating set is closed under taking inverses. I didn't do this here in the description in detail because it just would have made it more complicated, but that is an implicit assumption here. But again, for finite groups, you don't need to do this. So what we do is we start with one point, we run through all the points we have so far, map them under all the generators. If it's new, we're adding it to the list, and we do this as long as we don't get any new points, until we get no new points. The cost of this is the length of the orbit times the numbers of the generators, because I'm mapping every orbit element under every generator. And if this stops, it is the full orbit because there can't be any further element, since that it would be the image of omega under a word in generators, and all words in generators are taken care of by this iterated process. So that's for calculating an orbit. The reason I wrote this algorithm out in so much detail is because that way the variance for stabilizer and transporter, I think, can be easier understood. So that's just calculating the orbit. But I might not want or just the orbit. I might want, for example, the stabilizer, or I might want to find transporters. So let's first look at the question of transporter elements. And T can stand for transporter or for transversal, because the transporter element, here it stands for transversal, because what I will use is the fact that the elements of the orbit are in correspondence to cosets of the stabilizer. Each element in the same coset maps the point omega to the same image, and if I have two elements in the orbit, I just need to take the quotient of the two transversal elements for the corresponding cosets. These quotient will map from the first element back to the original point and then to the second image. So how do I get these transversal elements? I start the transversal element for omega itself. There's the switch. So the transversal element for omega itself is the identity. That's the element which maps omega to omega. And now, whenever I get a new element, I basically know how do I get this new element gamma from omega. Well, I know already an element which mapped this new element is obtained as image of delta under a generator. I know already which element maps little omega to delta, namely that's the transversal element for delta. And I therefore know, because gamma is the image of delta under the generator gi, that the transversal element for delta times gi will map omega to delta. So that's how I can construct such a transversal. Yes, and then the general case, as I said, is just quotient of transversal elements. This alone will not work for large groups or for very large orbits, because there is much extra storage cost, but it will be a crucial building tool for more complicated algorithms where when we build, where we will use shorter orbits to take the group apart into pieces. So next question is stabilizer. So how can we find generators for the stabilizer? And what we're using there is Schreier's lemma, which is basically as made for this case. Schreier's lemma tells us that if we have an orbit of a point and we go through all pairs of elements, we go through all pairs where we have an element delta and a generator gi in the orbit, and that the image of delta under gi will be another element in the orbit by definition of the orbit. Well, it will be the element gamma. Gamma will have a corresponding transversal element. And of course, if I take delta, the image under gi, that gives me gamma, and I divide off the transversal element for gamma, that is the element which would map omega to gamma, that will map delta to gamma back to omega. sorry, from omega to delta to gamma back to omega. So that is clearly in the stabilizer. Schreier's lemma says, actually, if I do this systematically, these elements together generate the stabilizer. And so what I just need to do, I need to collect these elements together. That will give me a generating set for the stabilizer. The slight problem with it is, well, it's actually not just a slight problem, but that's is a fundamental problem for a lot of the algorithms. If you just count how many generators you get here, that's again length of the orbit times number of the generators of the group. Some of them will be identity automatically if we are in the case where gamma is a newly defined element of the orbit, because then I'm not in the algorithm, I'm not even doing it, because that would automatically become the identity from this definition, but I get a lot of generators. And therefore, many algorithms need to have the fundamental problem of how to reduce this number of generators, and we will encounter that problem a couple of times. So, let me briefly show you how group actions in GAP work. And again, all actions are from the right. GAP always acts from the right. That is built in from the very bottom. And there is basically no way without rewriting the system fundamentally that one could put in left actions. So if you really, really need left actions for your applications, you need to convert them to a right action by, say, acting with the inverse of the element, or things like transposing matrices. Yeah, the commands are orbit, takes the orbit of a point, orbits, all orbits on a domain. There are these two functions, orbits domain, orbits takes elements possibly as seeds, but does not assume that the set given is closed under the action. Orbits domain does this and then works faster. Stabilizer, clear representative action is the transporter element. Action would be the permutation image of the action. I didn't write this out in detail, but if I keep track how would the generators move the points, I can write down the permutations for the action on the domain. And similarly, I get a homomorphism for the action. And all of these operations basically get as arguments first a group, and it will act through the generators of this group, then a domain, the set omega. In some cases, one doesn't need to give it, but if you give it, it can help improving performance. The point of which to calculate the orbit or the stabilizer, or a list of points which are of which to take the orbits. One can give a function as last argument, which describes the kind of action. And that's in situations where it might not be clear a priori how you want your group to act. For example, if you have a list of points, that list could be a tuple, or it could represent a set. And the image of a tuple is different than the image of a set. Well, you apply the group element to all elements, but your equality of objects is different. And therefore, for example, such operations exist. That's also the way how you could implement your own action on objects, which GAP hasn't even yet thought about. If you build your own objects and you want to have a group acting on them, that's the way how you can implement the particularity of your action. So just to give some example, here I take the symmetric group as 4. I calculate the orbit of a point. It's not sorted. It's given in the order as it finds the elements. I could take the orbit if I take the action on sets. That takes a sorted list and interprets it as a set of the elements. So here, the 1, 2 would be the same as 2, 1 because I just interpret it as a set. I can calculate the orbit here. I could calculate a stabilizer, transporter elements that will return fail if I can't transport. Action homomorphism would give me a homomorphism where the image is a permutation group. And I could use orbits, would give me all orbits as lists. So this would be the action of the dihedral group D8 on pairs of points. I get 2 orbits. One orbit is the edges of the square. The other orbit are the 2 diagonals if I label the corners 1, 2, 3, 4. Yeah, so that's some basic example of how these group actions work. They will basically always work even if you implement your own action function. However, if in some cases there is special mechanism in there, for example, if you have a permutation group acting on sets or tuples of points and you calculate the stabilizer, it doesn't just call the orbit algorithm. It tries to do something more clever, which works faster and uses less memory to calculate the stabilizer. Generically, this is using the orbit algorithm as I gave it to you. Yeah, some more examples. If action on sets would give me the permutation image. I could have a group acting on its own elements by conjugation. This group has 24 elements, so I get permutations of degree 24. Can calculate the orbits. That's basically would correspond to the conjugacy classes. Can calculate, and that action is the action. If I don't give an action function, the action is through the caret, the het operator, which in a group does conjugation. If I want the action by right multiplication, I would have to specify this. Yeah, what else am I? Why do I do conjugacy classes of? Why am I doing this? So that would give me representatives of all subgroups up to conjugacy. Oh, when I could calculate their orbits or could calculate action on subgroups, yeah. Okay. Let me mention 2 variants of this, of the orbit algorithm, because they encounter them later. One is, okay, so if the group acts on an algebraic structure, and I take an element of the algebraic structure, calculate the orbit, it often is meaningful to look at the substructure generated by the orbit. For example, that's how you get normal subgroups. That's how you get submodules. How do you do this? Well, you do the orbit algorithm, but you always look at the substructure generated by the orbit so far. And if the new element in the orbit is already in the substructure, you really don't need to consider it anew because it is already generated. So that's how one, for example, can calculate submodules. That's how one can calculate normal closure of a subgroup. The other variant has to do with group orders or stabilizer orders. So a big problem which we will encounter again and again is the total number of Schreier generators is huge. If you have a group with 2 generators acting on a set of order, well, or with an orbit of length 100,000, you will get roughly 200,000 Schreier generators. And your calculation essentially will choke on the number of generators. Just processing them takes a lot of time. And therefore, it is often preferable that we don't want to look at them all, or we want to be able to say, look, I have enough, I don't need more. Yeah, this is, imagine this is like when feeding a baby. The baby would love at some point that there isn't another spoon and so forth forced into the mouth. So the system would like to do and say, I'm done. And indeed, one can do this. This doesn't have a specific interface, but various versions of orbit algorithms, stabilizer algorithms have this built in, and it's crucial for performance. And how can this be used? For example, so let's assume we know the order of the group, and we can calculate orders of subgroups. If we calculate an orbit, typically what will happen is that we calculate new images. The orbit grows very quickly. We typically relatively soon have the whole orbit, but in the algorithm, just to make sure there isn't anything missing, then need to map still every orbit element which we haven't yet processed under all the generators. So even if you just have 2 generators, that doubles the cost. If you have more than 2 generators, that multiplies the total cost by this factor to the length of the orbit. But what we can do is say, if we care about the stabilizer, if we have the whole, well, or if we have part of the orbit, we get some Schreier generators, and we take the subgroup generated by them, and we find the order of this subgroup times the length of the orbit we have so far is the group order. Then we know we are done, right? Because there can't be more in the orbit, because then the stabilizer would have to be smaller. There can't be more in the stabilizer, because then the orbit would have to be shorter. And one can use this to speed up the calculation by basically stopping at this point, knowing, okay, I got all, I will not get anything more, even though formally I would have to process them all. The other variant, and that is in cases of very, very large orbits, and this is something which is typically more probabilistic argument and can be difficult to, a bit more difficult to handle, but might give an indication about stabilizers. So, how do we get the Schreier generators? We get them from a coincidence, right? We need to get, if we get, the first time we get a new point gamma, that point, that transporter element, the transversal element for that point is just the transversal element for delta times the generator GI. That does not give us a new Schreier generator. We get the Schreier generators if we get the same orbit element a second time, a third time, and so forth. So we get a coincidence. And if we, well, there isn't a proof that they should arise randomly, but if we would, if as a assumption, one makes the guess, oh, let's assume we would get elements of the orbit randomly, that is basically the situation of the birthday paradox. I'm sure you've seen this question as a problem posed often in a combinatorics class or a statistics class. What's the probability that 2 people in a room have the same birthday? Yeah? And it turns out it's roughly the square root of the total number is needed to get such a coincidence. So, if you start calculating an orbit, and the question is, how many, when should you expect coincidences? Well, you should expect coincidences at about the square root of the orbit length. So if you start calculating an orbit, and it is too big to store the whole orbit, if you keep track when you get your first coincidence, and one can make this fancier by counting when do you have the first few coincidences, this gives you a guess how long the total orbit is. even if you don't write it out. And if you take the stabilizer generators you have so far, and they times this prospective orbit length would be the group order that you might take as an indication, but it is not a proof, and GEP will not use this really to prove things. But in an experiment, this might give you an indication about length of very long orbits, which are longer than one can calculate. These variants, they are not all built into explicit functions. Basically, I have found that almost every time I need an orbit algorithm, I end up re-implementing it because I need a variant slightly different than the one which is built in. And that's why I went into so much detail with the orbit algorithm. While there are the built-in functions, if you build something on using orbit algorithms, you might find yourself re-implementing the orbit algorithm as well. Yeah, and that's why I gave it here. Okay. Yeah, and that was basically my first lecture.